Hey everyone. So for our EE373 final project, Tim and I decided to make a restaurant recommender using offline contextual bandits. And basically, the idea is this. Apps like Belly are able to recommend a restaurant you might want to eat at next, given your previous history. And we want to do something similar. So given the current time of day, day of week, and your user history, we want to be able to recommend a restaurant you do want to eat at. So for this, we use a Kaggle data set of real New York City check-ins to all types of venues. And this had around 220,000 check-ins across all New York City venue types, things like gyms, offices, parks, and so on. So we filtered it by food venues here and got around 50 food matching keywords like restaurant, pizza, cafe, and bar. And we use this category as labels. And this left us with a lot less check-ins and roughly 15,000 unique check-ins that we could use. And then next was location here. And we don't really want to recommend a place to Brooklyn when somebody's in Midtown. So we divided New York City into roughly 500-meter square grids using latitude and longitude, and each check-in was assigned to a cell. And recommendations were restricted to restaurants within roughly a 1 kilometer walk, so 2 cells. And this removed restaurants with fewer than 3 total visits, so every recommendation had at least some history. After filtering, we had about 7,000 candidate restaurants, and each event still had around 450 nearby options on average, and that makes the prediction problem pretty hard here. And we also built a per user history. And for each check-in, we check the last three restaurants they went to and the time of day that they went to, and we can better capture patterns like repeat visits or stable food preferences. And we also had a bandit formulation. So we formulated the problem as a contextual bandit, essentially a one-step MDP. The state includes the user, time of day, grid cells, and the last three visits. And here the actions are things like choosing restaurants from the nearby candidates. The reward is one here if we match the restaurant to the user, to the one the user actually liked, and zero otherwise. We tested a soft reward that gives zero credit for predicting the correct food category, but since we couldn't deploy it live, we treated one as historical check-ins, and we used a simulation for that. And we also did a 80-20 test split by time, and this was by time so that the training always comes before testing. Okay,
We
you're good.
tested three approaches against the popularity baseline, which simply recommend the most visited nearby restaurants. First, we used logistic regression, which combines user context and restaurant features, training on positive visits paired with five randomly sampled negatives. Second, we tried a soft reward variant. This downweighted same category negatives to zero point 0.5 instead of 1.0, giving the model a denser learning signal. Third was LinUCB, a contextual bandit algorithm. It scores restaurants using a predicted reward plus an uncertainty bonus, which encourages exploration. It processes events sequentially to determine a real online system. Before offline evaluation, we set alpha to 0 for pure exploitation, since we cannot actually observe what would happen. Here's what surprised us. The popularity baseline hit 8.8% top 1 and 21.8% top 5 accuracy. Logistic regression with soft rewards was the best performance, with 8.8% top 1 and 21.4% top 5. LinUCB came in at 8.4% and 20.8% respectively. The personalized models barely beat or just tied the popularity baseline. Three major challenges caused this. First, massive candidate sets. With 547 options on average, it's extremely hard for any model to pick the exact right spot. Second, sparse user histories. Many users has fewer than three visits, leaving models with mostly zeros to learn from. Third, LinUCB lost its main advantage because exploration bonus only pays off in the live system. Ultimately, popularity is a very strong baseline. While our other models learn meaningful patterns, the offline setting masked their true potential. If we continue this, we would combine the soft reward signal with LinUCB's training loop and try a neural contextual bandit to capture the nonlinear interactions.